Today, we're going way beyond just simple 3D models. We're diving into how to build intelligent, living digital copies of our physical world. Think of this as a playbook, really, for you, the AI engineers who are literally building the future. So, here's the big question, right? How do you give a building a living digital brain? It's the central challenge facing AI and civil engineers. We're not just talking about creating a pretty static model, a digital sculpture. No, this is about bringing that model to life, giving it senses, the ability to think, and even predict what's going to happen to its physical twin. Okay, first things first, we need to get a key distinction straight, and this is absolutely fundamental if you're doing research in this space. You've heard of a building information model. It's an incredible blueprint for sure, but a digital twin, that's our focus today. That's the living, breathing avatar. It has a pulse. It's fed by a constant stream of real time data. So remember this.
BIM is the blueprint. The digital twin is the living, breathing system.
Start with the blueprint, then we'll build the skeleton by capturing reality in 3D. After that, we connect the nervous system, and that means tackling the huge challenge of data sharing. And finally, the best part. We get to your role as an AI engineer, giving this thing a brain. Let's get started with genetic code of our digital avatar. You might think every great digital twin starts with a brilliant line of code, but it doesn't. It starts with a plan. This is the genetic code for our avatar, and the definitive guide, the one you absolutely need to know, comes from the Pennsylvania State University's Computer Integrated Construction Research Group. Seriously, if you're in this field, it's required reading. So, what is this plan really? It's a super detailed formal document that spells out exactly how the digital model is going to be built, used, and maintained through its entire life. And trust me, this is not just paperwork to be filed away. It's a mandatory script. It makes sure everyone from the architects to the contractors to the people managing the facility years later is on the exact same page about who does what and how all that critical information flows. And the Penn State Guide breaks it down into a really clear 4-step process. First, you have to identify your goals. I mean, what's the point? What do you actually want this model to do for you? Is it for design checks, energy analysis? You got to know that first. Then you map out the workflow. Who does what and in what order? Next up, you figure out the data exchanges. Who creates the data, who needs it, and when do they need it? And finally, you get down to the nitty gritty, the tech. What hardware, what software, what networks do you need to pull this whole thing off? And what's just incredible when you look at it is the sheer scope of a proper execution plan. I mean, it covers everything. We're talking high level project goals, all the way down to the tiny details of quality control, like checking for clashes between pipes and beams. It even specifies the exact hardware and software everyone's going to use. Get this wrong, have a weak plan, and you've got a weak foundation for your entire digital twin. It's that simple. Okay, so our blueprint is solid. Now it's time to build the avatar's skeleton. And that means creating a hyper-precise, as-is geometric model of the real world. To do that, we need to get into some serious high-fidelity data capture. And the go-to technology here is mobile laser scanning, or LiDAR. And get this, these systems can capture over 1 million data points per second. It's just wild. What you get is this incredibly dense 3D point cloud, which is basically the exact geometry of the environment captured in stunning detail. But, and this is a really critical insight from NCHRP Report 748, you don't always need that level of insane detail. It all depends on your goal. If you're doing a high precision engineering survey, yeah, you need crazy high accuracy and a super fine point density. But if you're just doing general asset management, you can get away with much lower accuracy. The takeaway here is huge. You have to plan your data capture to match your goal. Otherwise, you're just creating massive costs and a mountain of data you don't even need. So, how is this magic even possible? Well, it's a whole suite of technologies all working together in perfect harmony. You've got a GNSS receiver for its global position, an inertial measurement unit, an IMU, to track every little tilt and turn of the vehicle, the laser scanners themselves, of course, and high res cameras. All of this tech works together to precisely georeference every single one of those million points per second in 3D space. It's a beautiful symphony of sensors. Okay, but think about it. A perfect skeleton is pretty useless if it's just a pile of bones, right? It needs a nervous system to connect everything. And that's our next huge challenge, building that nervous system. This means making sure data can flow seamlessly between different companies, different systems, and some groundbreaking research from Carnegie Mellon done for the ASCE Data Sensing and Analysis Committee really shows us just how hard this is. So you'd think the biggest problems with data sharing would be technical, right? Wrong. A survey of folks in the industry shows the biggest barriers have nothing to do with tech. It's all about business and policy. Companies see their data as a competitive edge. They're, deeply concerned about privacy, and they're really worried about the legal and ethical blowback if they share something they shouldn't. And this quote just hits the nail on the head. It perfectly illustrates the core dilemma. It's from a survey participant at a national laboratory, and it just captures the raw fear that sharing data could expose not just their own weaknesses, but the vulnerabilities of our critical public infrastructure. So, how do we fix this mess? Well, that same research points to a pretty clear roadmap. And again, it's not about inventing a new piece of tech. The top strategies are all about building trust by creating clear rules of the road. Number one, establish rock solid industry protocols and data use agreements. Number two, create data standards that everyone agrees on. It's only after you get that policy and business foundation right that the technology can really do its magic, which brings us to the final and maybe the most exciting step. This is where you, the AI engineer, come in. This is where your work becomes absolutely critical. We have the blueprint, we have the skeleton, we're building the nervous system. Now it's time to build the brain, and this is the payoff for all that hard work. When you have a well-planned, high-fidelity, fully interconnected stream of data, you've created the perfect playground. It's the ideal foundation for you to develop and deploy powerful AI applications that can actually create real tangible value from that digital twin. I mean, with this foundation in place, just think about what you can do. You can build predictive maintenance systems that analyze sensor data to see a failure before it happens. You can completely automate construction progress monitoring just by comparing daily 3D scans to the plan. You can run these incredible what if simulations to optimize a building's energy use without ever touching a real thermostat. This is what turns a static model into a powerful active tool for making smart decisions. So, there it is. After laying the foundation with the blueprint, building the skeleton, and wiring up the nervous system, this is what we've built: a true digital twin. It's not a static model anymore. It's an active learning system that mirrors, and this is the key, predicts the behavior of its physical counterpart. So, what does this all mean for you as a researcher in this field? It means the future of our world, our infrastructure, it's going to be defined by data and code just as much as by concrete and steel. So, the final question I'll leave you with is this: what part of that code are you going to write?